Okay, so now I'm going to hit you with one new idea, and then I'm going to ask you how to think backwards. These are some of the harder types of probabilities to determine. A little bit more advanced thinking required here. But the math isn't the hard part. It's straining your imagination a little bit. The first idea I'm going to throw at you is the idea of what's called the complement. Now the complement with an E, not an I, complement with an I means you look great today. Complement with an E means the opposite of what you're thinking about. Not necessarily the opposite, but sort of the part you're not talking about. Let me give you a math example. The complement of, say, well, let's say there's a probability of an event. Probability of an event is 3 out of 4, 3/4. 3 out of every 4 times you try something, this event will happen, okay? The complement of the probability of E is 1 minus 3 out of 4, or 1 out of 4. The probability of E is the probability of this event happening. The complement is the probability of that event not happening. And sometimes when it's hard to find the probability of an event, it's a little bit easier to find the probability of that event not happening and then subtract that from 1. If the weatherman says there's a 70% chance of rain, it means he's also saying there's a 30% chance of not rain. Okay, the complement is the probability of whatever you're talking about not happening. And you find it by subtracting the probability of the event happening from 1. So that's the complement. We're going to use that here because otherwise this math would be difficult. There's one other idea I'm going to hit you with. And this idea is called the counting principle. The counting principle says if you have a series of choices, your total number of choices is determined by multiplying the number of choices in subsequent events by one another. So for example, if I have 2 shirts and 3 pairs of pants and 5 shoes that all match, I have 2 choices of shirts to wear, 3 choices of pants to wear, and 5 choices of shoes to wear, and they all match. I would multiply these together, and I would have 2 times 3 is 6, times 5, I would have 30 outfit choices. So the idea behind the counting principle is that if you have choices, multiply the number of choices together to get a total count of your final number of choices. The idea behind the complement is sometimes it's difficult to determine a probability of an event happening, so you determine the probability of the event not happening and subtract that from 1. Let's see if either of those ideas are helpful in this first example. A basketball player has a 50% chance of making each free throw. What is the probability that the player makes at least 11 out of 12 free throws? Okay. Sometimes I like to start with the denominator, the sample space. How many things can happen? It can be useful to think of this as a choice. Now in real life, we don't always have a choice of whether or not the ball goes in the net. It's not up to us. That's why we have probability to try and figure out what's probability of these events happening. But pretend for a moment you had a choice, okay? If you could pick how your sample space played out, then for the first free throw, you would have a choice between succeeding or failing. There are 2 things that can happen. The ball goes in the net or the ball doesn't. You would then retrieve the ball, go for your second free throw, and again, there are 2 things that can happen. If you were in control, you would think of it as 2 choices. I can choose for the ball to go in the net, or I can choose to miss. For your third free throw, you would again have a choice of 2 outcomes. It becomes a little bit like your outfit choices. you multiply your subsequent choices together to determine what the total number of possible outcomes are. And so when you're making 9 free throws, when you're trying to make 9 free throws, 11 out of 12 free throws, you can picture it as if it were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 choices. There are actually 2 raised to the 12th power ways that this can go, and that is a lot of choices. 2 to the 12th power. So we can have a lot of choices on how that works. I'm going to bring up my calculator, which accidentally got shut down. And in a moment, that'll be ready. And we'll figure out what that number is. I just want to double check it. So that's a sample space. Sample space, again, is going to be our denominator. So that's what we started with first, because that was kind of the easier idea. Now, let's get to the more difficult idea, okay? Slightly more difficult idea. First, let's bring up our calculator. And let's just double check that 2 to the 12th. How many different ways can this happen? 4,096. So our denominator is going to be equal to 4,096. Let's talk about our numerator. Numerator, our event. Okay, this is going to be the tricky part, and I think I'm going to need even a little bit more space to talk about it. So hopefully you guys can still read that. And let's see. Our event. Okay, probability that the player makes at least 11 out of 12 free throws. Now, if you think of this as one big experiment, we would add up all the different events. First, there's the event. Because we're going to say at least 11, okay? That means they want to know the probability. Well, probability of him making 11 or 12 of these free throws, right? Okay, so we need to find the probability of him making 11 or the probability of him making 12. We need to be able to count the number of ways that can happen. The 12 is kind of the easy one. There's only one way to make 12 free throws, and that is if you're deciding between success and failure. We all wish we could actually decide this thing, but you could succeed on the first free throw, succeed on the second, succeed on the third, succeed nine more times. There's only one way to do this. You make every free throw. If you could choose, you only have one path to a 100% success rate. Okay, so this is the one way to get 12 successfully in. Thinking backwards, thinking in complements, thinking differently, that can help on this. How many ways can you make 11 out of 12 free throws? Let's not try to count all the ways you can make 11. Making 11 is the same thing as missing one. If you have 12 tries, succeeding 11 times is the same thing as failing once. Well, if we were going to fail once and we could pick the number of ways to do it, we could fail on the first one, and we could make the next 11. Or we could fail on the second one, make one, succeed once, fail once, and then succeed the remaining 10 times. We could succeed twice, fail the third time, and again, if we could choose this, if we were in control, we could choose then to succeed 9 more times, and I could keep playing this game. But what I'm hoping you'll see is the number of ways you can fail once is really just a choice of where you would place the failing free throw. And there's only 12 places to put it. You could fail on the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. There's only 12 ways to do this. It comes down to counting. So there's 12 ways to make 11 successful free throws. That's all they're asking for here. Okay, at least 11. What is the probability the player makes at least 11 out of 12 free throws? Another way of asking this is, what is the probability of making 11 or 12? Well, it's the probability of the 12 ways, that you could make 11. In other words, the 12 ways that you could choose to fail once, plus the one way, the only way that you could choose to succeed 12 times, divided by 4,096. So there are 13 ways to do this, and 4,096 ways total to have 4,096 different outcomes of making 12 free throw attempts. There's one way to make all 12. There's 12 ways to fail on exactly one. So there's 13 ways total to make 11 or 12 free throws successfully out of 12 tries. It's 4,096 things that can happen when you're faced with a binary choice 12 times in a row, because you multiply the number of choices you have together. That's a challenging probability problem to set up. Do one more like this. A test consists of 9 true-false questions. A student who forgot to study guesses randomly on every question. What is the probability that the student answers at least 2 questions correctly? At least. So that could be 2 questions correctly. That could be 3 questions correctly. That could be 4 questions correctly. It could be 5 questions correctly. Now, we could find the probability of all of those events and add them all together to see how this one big experiment goes. But we're not going to do that. We're going to use the complement instead. I'm not going to find the probability of correct being greater than 2. That seems hard. Instead, I'm going to find the probability of only getting 0 or 1 correct. This is a little bit easier. Okay, so I'm not quite going to answer this student's question directly. I'm not going to figure out all those different probabilities and add them up. I'm going to answer a simpler question. And again, one way to think of this is, if you were in control, how many ways could you do it? Okay, so you're staring at 9 choices. Let's look at the denominator again. The denominator is always the number of things in your sample space. So the sample space here is the number of choices you have. Look at the first question. You have a choice of true or false, like on the free throws. If that was something you could choose to succeed or fail. Here, you can pick true or false. On the second one, you can pick true or false. Third one, true or false, and so on 9 times. And just like with your outfits, you multiply these 9 choices together. 2 things you can do, 2 things you can do, 2 things you can do, all the way out to 9 choices. So our denominator is 2 to the 9th, which is 512. Which I suddenly can't seem to write in order. Let's try that again. There are 512 total ways you can hand in this test. Seems like a lot. These numbers always seem large. If the number seems large, it doesn't automatically mean you're on the wrong track. Counting things, the numbers get bigger faster than you think. Now let's look at the numerator here. Okay? How many ways can I get 0 correct? Well, okay. Let's see. The probability of getting 0 correct is, well, let's not even look at that yet. We're not doing the probability yet, we're counting. the number of ways to get 0 correct is you put the wrong answer down every time. Now, if you didn't study, you can't really do this intentionally. Okay? This is, again, we're pretending that we have it in control. We're pretending that these are choices, because that simplifies the way we think of the math. But if you were deciding to get all of these true-false questions wrong, there's only one way to do it. You decide to put the wrong answer down every time. Again, I know you're guessing and you can't really decide, but if you could decide, that's how you count how many ways you could do it. Now let's count the number of ways to get 1 correct. Well, if we were in control, we could decide to get the first one correct. And then we could choose to get the rest wrong. If we were in control, we could choose to get the second one correct. And then put the next 7 down as wrong answers. If we were in control, we could choose to get the third one correct, etc. There are a total of 9 places to put your 1 correct answer, which means there are 9 ways you can get 1 correct answer. So the probability of getting 0 or 1 correct is the 1 way to get all of them wrong, plus the 9 ways to get 1 of them right, divided by the 512 ways there are to fill out a true-false test with 9 questions on it. So that's 10 out of 512, which reduces to 5 out of 256. It's a small probability. Okay, so if you guess, you're not particularly likely to just get 0 right or 1 right. Probably can do better than that. But this wasn't the question. The question was, what's the probability of getting 2 or more correct? At least 2. That's 2 or more. Well, these are complements. What this means is either one or the other has to happen. And the probability of this happening and the probability of this happening have to add up to 1. Okay? Something's going to happen. You're either going to get 0 or 1 correct, or you're going to get 2 or more correct. There's really no other option here if you're just guessing on a 9 true-false test, 9 question true-false test. So the probability of getting 0 or 1 correct is 5 out of 256. The probability of getting 2 or more correct is 1 minus 5 out of 256. You can plot your calculator and make this a percent, or you can remember that 1 can be written as 256 over 256, and you can subtract fractions with the same denominator and write 251 out of 256. This is the answer we wanted. But to directly compute all the different ways you could get 2 correct, and then 3 correct, and then 4 correct, and then 5 correct, and then 6 correct, 7, 8, 9, that would take a while. So instead, we directly compute the number of ways to completely fail this test. It's only 1. We directly compute the ways to only get 1 question correct. There's 9. We add those together, and we find there are 10 ways to only get 0 or 1 correct out of 512, which is the same as 5 out of 256. Well, if there's 5 out of 256 ways to get 0 or 1 right, then there's 251 out of 256 ways to get 2 or more correct. We weren't looking for this 0 or 1 correct probability, but it was a lot easier to find. So we found it, did 1 minus that, and then found the answer we really wanted, which is the probability of getting 2 or more questions correct. I hope this was clear. Again, these PDFs will be available on the website so you can look at them rather than having to refer back to this video. And now we'll go on to talking about expected value, fairness, and then how you're going to design your game.